Or maybe while we're waiting, we could do some intros. See, there's a
Yeah.
couple names in here I don't recognize. So I'll kick it off. My name's Nissan. I work at Netflix. I'm one of the core Metaflow contributors, co-hosting officers along with Sabin. Yeah.
Hi, I'm Savin. I work at Outer Bounds on Metaflow.
I am Lewis. I work at Ray.
Hello, I'm Saurabh. I work at Outer Bounds on Infra and Metaflow.
And Joseph. All right. Oh, sorry. All right. We can start taking away. So welcome everyone to this third instance of the office hours this year. Pleased to welcome Lewis from Robotics and AI Institute. Couple housekeeping notes. This talk is going to be recorded and uploaded to YouTube afterwards. We have a Slack channel, Ask Metaflow. Please join and continue the discussion there if you have any other questions. And like and subscribe to our YouTube and GitHub repo. All right, without further ado, Lewis, take it away.
Thanks. I'm Louis Sano-Espinosa, and I'm going to be talking about how we're using Metaflow at Ray. So just as a quick start, our mission is to solve the most important and fundamental challenges in robotics and AI, and that sort of drives a lot of what we do. We are, oops, I think this took a little while to load. So our research is quite varied. Here's some public examples of stuff that we've done. We've built this like autonomous bike that will do BMX bike tricks and such. I think if you scroll past here, it'll jump over onto a picnic table. All this is done via reinforcement learning. We've trained the Boston Dynamics Spot robot to run much faster than it can normally. I think this is the normal pace, and then later on you can see it kind of doing a weird gallop thing. Again, that was done via reinforcement learning. And then also we've sort of worked with Boston Dynamics to help make the humanoid robot do more sort of like lifelike motions. These are just sort of a few examples of our research, and later in this presentation, I'm going to talk about how we're leveraging Metaflow to help achieve some of these results. Okay, so some challenges about working at a research institute that I've noticed. You know, this is my first time in a sort of a research organization. So there are multiple parallel research directions, and they don't all necessarily have a common ground between all of them. And we're sort of a large organization kind of sprinting towards different directions. There's a huge variety of problems across multiple different subject areas. And there's sort of massive compute and storage requirements, and the resources that we have available to us can be constrained depending upon what features you might need for a particular use case. And then researchers tend to have a sort of a varied level of infrastructure and engineering capability. Researchers are really experts at their particular subject areas and aren't necessarily interested in building getting into the weeds of some of the tools that we're doing or we need to use. Some of the growing pains that I've noticed while working here is that we have several data centers with different combinations of hardware depending on the features that we might need to support the research. We use Google Cloud for flex capacity for everything that doesn't really need a specialized resource like an H100 or something like that. We rely very heavily on Kubernetes, and from an infrastructure perspective, this simplifies the resource allocation process and how everything is administered. You can kind of do everything, sort of handle everything the same way, no matter where it technically is located. People have somewhat of a tendency to use compute resources as pets. They tend to keep them around for a long time. They might have like a love affair with a VM, and may even reserve like huge parts of the cluster for days at a time, just in case they might need it. Sort of like misusing the allocation of resources that we have, and it's kind of typical in like a research environment where you don't necessarily have the background in ephemeral compute. Sort of another growing pain that I've noticed is just the general Kubernetes experience. Sort of the vision, I think, is you have this platform that's self-service with perfect, efficient resource allocation. The organization can control, how to roll out new hardware that the company can use and scale, and you'll have efficient cost optimization. The reality of this is that from a user perspective, you kind of end up in YAML hell, where you're creating a bunch of manifests to define specific things that maybe you don't understand. And all this is sort of a distraction from the higher level goal, and sort of takes you away from the research that you want to work on. So that's when we started thinking about how, our team as a platform team, how can we accelerate research? Primarily we're doing this by building and using tooling that takes care of the plumbing for our users, allowing them to focus on the most important goals for the organization. I really like this image from the Metaflow website that I think depicts like a thing that I've seen everywhere, where researchers, data scientists, typically care about the sort of modeling and algorithms part of the process that they're working on the most. And there's sort of like a inverted pyramid in terms of like how much infrastructure is required to support that development. I think that Metaflow does an amazing job balancing all of these needs and providing a higher level system that allows us to organize these core components. We really liked that Metaflow was open source, with a company like Outer Bounds supporting a paid product, and sort of Netflix contributing to it. We knew that we could start small and move pretty quickly with the open source product, and then as we grew or needed additional capacity, we had the ability to partner with Outer Bounds or the open source community to achieve our goals. And if anyone has any questions, feel free to stop me. So at a high level, our architecture looks like this. At the bottom, we have a few data centers in addition to Google Cloud that provide the raw resources, compute resources. And on top of that, we have Kubernetes providing a API abstraction over all those resources. And then to balance the resource allocation, sort of prevent people from camping on compute, we've added queue on top of that, and that helps us fairly distribute resources across very different tasks. And sort of these three things provide the foundation for everything that we're doing. And then on top of that, we have a bunch of workloads that are either running Ray or just Python or some other type of processing. And this is all orchestrated via Argo workflows in conjunction with Argo events, sort of creating the jobs and such. And then it's kind of the most user-facing thing that people are using is sort of the Metaflow system, where we're using that to create workflows and sort of build the things that are under it. Let's go. Then I'm going to go over some use cases that I think are interesting and how Metaflow helps support our research. So we have this sort of data curation pipeline where we're taking video from these gripper devices. The data collector performs a series of tasks that we intend to turn into a training data set. For example, the collector might use the gripper to open a bottle or drink from a teacup, and the device will record a bunch of raw video and sensor data, and that gets uploaded to our platform and then needs to be processed in order for it to be usable for training. So the user of this pipeline will kick off the process by providing an input that corresponds to a set of IDs that correspond to uploads. The pipeline will then proceed to download that data, kind of parallelize this effort across many different nodes, process this data into so that it's useful. So for example, it does like tag detection, detects like estimates the width of the fingers in the video, generates a world map of the scene that is in the video, creates camera trajectories using tools like HLOC, GlowMap, or SLAM. To do all of that, does some localization, and then sort of finally generates this data set that can be used for a training process. This pipeline uses a ton of research library collaborations with universities, and it all needed to be flexible enough to kind of be able to use this somewhat hard to use research code. And Metaflow allows us to scale this pipeline pretty effortlessly to process 500 gigs of data at a time, running thousands of tasks in parallel without really skipping a beat. To give you an example of what that looks like from the Argo Workflows UI, which sort of lets you see the fan out a bit better than the Metaflow UI. This is just an example of a small run of this task. Another cool example that we have is we're using Metaflow to implement regression testing for our models that are built in the Isaac Lab simulation environment. In this particular flow, it accepts a sort of before commit and after commit. The flow will then start sort of two parallel processes for the before and after on two different clusters, and we'll run all of the training tasks available for those commits, and then compare the results between the two. The workflow will completely manage the lifecycle of the external cluster that was created, the Ray cluster that was created, and record the metrics across each of the stages, and creates a report in 1B that the user can use to determine if there was a material impact in the changes in the code base. This pipeline and this testing system is completely self-service for our users. They can configure and manage this without really our involvement. And it's allowed us to be able to move between major versions of our simulator without sacrificing any sort of model quality. Our goal for this pipeline is to have it be running continuously 24/7, so that we'll have really fine-grained data about the quality of our models. And the team that sort of built this section believes that this wouldn't have been possible using any other tool, especially as fast as they were able to do it, which probably from concept to production was under a month of time. Another cool use case is using Metaflow as a backend. Oftentimes you have many flows that have tons of runs, and each run has tons of tasks, and it's kind of hard to gather any useful information from at a high level from that specific the raw data. And it's more useful to probably take a higher level view of the results that were generated and do a broader interactive analysis. Metaflow, by providing a really nice client API, makes it super simple to create customized applications that can collate results from multiple runs and then display it in a way that's useful for the researcher or user. In this particular case, we created a Streamlit application that allows the researchers to query for specific results, compare the sort of video data and other metrics, and be able to sort of freeform analyze the results. And all of it, this is pretty much only uses the Metaflow client API as the backend. and was also similarly pretty trivial to build, given how well structured that system was. Here's a more sort of typical data engineering task where we want to do a bunch of data processing and conversion whenever a particular upload is sent to our platform. So in our system, whenever a user submits an upload, this triggers an event in GCP, and that gets submitted to PubSub. In our GCP PubSub. And then in our Kubernetes cluster, we have an Argo event source that's listening to all the events that's published to that topic. We then do some formatting of that event so that it meets the convention that Metaflow expects. And then we forward that into the Argo events event bus. Then, since this flow has an @trigger decorator on it, when we've deployed it to Argo workflows, it will automatically create a sensor that's looking for that event. Basically, anytime this upload happens, it will use the information in the event to query the platform for additional data, relevant data, and it'll do the necessary processing. Like in this particular case, it's extracting video from this file format, creating Parquet files, and creating other data formats that are useful for visualization, and then uploading this all as a new data set in our system. So while all this has been, great from Metaflow, we've been able to achieve all of this in like less than a year, I think, using the open source product. There have been a few pain points that we've had, namely, we kind of need a try catch finally for flows. A lot of our flows have side effects in the infrastructure, like creating a PVC or creating an array cluster, and we need a way to make sure that these resources are appropriately deleted once it's the flow is done, or if there's an error to kind of kill that thing. I think that there's a way with the new release from Metaflow. I think there's a way to actually do this, which is highly appreciated. Another interesting pain point that I don't think is widely known is if you use a @card decorator in a highly parallel flow, that can cause unintended database load. When we initially deployed deployed Metaflow, we were using Cloud SQL, Postgres Cloud SQL as the database. If we had someone deploy a flow that was running 1,000 parallel tasks, it would basically lock the entire service. So no one else could access the UI, or no one could access the UI, and the flow would ultimately fail with timeouts on the database side. You can somewhat mitigate this issue by setting the card type to blank. And I think that when you do that, there's less queries made to the database compared to the default card. But ultimately, the way that we were able to solve this was by switching to AlloyDB with read replicas, and that has mostly completely solved our database issues. Another thing that we've run into is, needing, we don't really have a way to pass in dynamic values into a decorator. So like say, for example, we wanted to dynamically or programmatically create a PVC with a generic name, and then have another step in the flow. Use that PVC. There's not really a way to pass that in, as far as I know, or to be able to configure the amount of memory or CPU requested based off of some information that you have in the prior step. I don't think there's a way to do that. We've run into issues with the sort of horizontal pod scaling that's available. I believe that it only scales based off of memory and CPU utilization. And what we often find is that that tends to be quite low, at least in our setup. And the thing that is really the limiting factor is sort of the I/O requests on the database side that a given pod can make. And I've had situations where someone spins up a flow that has 10,000 parallel tasks, and the only way to sort of fix it is to bump up the replicas of the Metaflow service pod. And it would be great if we had a way to like automatically do that without requiring a person to go in and change things. And then finally, just sort of like a GitOps based way to deploy things has been more difficult than we expected. Whenever you run the Argo workflows create, it needs access to the cluster, the Kubernetes cluster, to be able to do that. And we haven't really figured out a way to do this the right way, I guess. In our system, we can't have GitHub actions that connect to Kubernetes directly. So it's been a challenge to figure out how to automate deployments. And that's all I got. Any questions? I'm happy to talk about any of these flows or any of my pain points.
No, this is awesome. I was actually on the last point about GitOps. If you could, like, what are you actually doing then?
We're just doing manual deployments, right? Like, someone has, someone has a flow. I mean, we're doing research, so it's not like, that. It's not like it's a production application, I guess. So people can just deploy things manually, and you can still have the appropriate controls with all the Metaflow knobs that it gives you, but it's not sort of automatically deployed, right? Like it relies on a user doing a deployment.
Yeah, that makes sense.
So on the topic of Metaflow service or like autoscaling that service, like what's preventing you from autoscaling it on requests?
I think metric service is just from. Actually, sorry, I didn't mean to.
No, you go ahead. I don't actually know much about, like, I set there's like a thing in the Helm chart that allows you to configure it, right? But I believe that it's only measuring memory and compute to trigger the scale. And our memory, I mean, I guess I could set the value to be really low. But I find that the memory or use and the CPU utilization to always be kind of low, and it never really expands as fast as the load that's coming in.
Yeah. So
yeah, I think for us.
Yeah, go ahead, Oleg.
Yeah, I would say, well, I think we actually scale on CPU. I think if we have HPA somewhere for this service, but anyway, I think what would be nice from our end, which was for a long time on the to-do list, is to export some more custom metrics out of metadata service for like Prometheus format than HPA or like metric server. You could scale based on them, because right now there's no, like, except for CPU and memory, like top level pod metrics, nothing is coming out of that pod. And it would be probably much nicer if we had something a little more specific and that makes more sense to scale on in those cases, maybe.
Yep. No, totally in agreement. I think the only reason why it doesn't exist is because we just haven't gotten to it yet. But yeah, if you're interested in sort of like, making a PR contribution, we'd be more than glad to take that.
Yeah, I mean, definitely interested. I think I just have to find out more about it.
Yeah. And then on the topic of dynamic decorators, there's definitely sort of like some work that we are exploring right now to make at least sort of like some of the attributes dynamic. And already for many decorators, like let's say the DBT decorator, there are things that are sort of like dynamic in nature, where the attributes basically reference a Metaflow artifact. So in a previous step, you could sort of like, basically set your templates or your projects, and then sort of like in the next step, we'll sort of like just
I think with the config, I think you can do stuff like that, right?
Yeah, so config basically binds everything and deploy time, or when you are starting your workflow, then everything sort of like gets logged in. But some of the work that we have done with DBT is more like the decorator's attributes are set right when that task is getting executed. So after the previous task is executed, because the previous task is indicating what values need to be populated.
Okay, cool. Yeah, that would be, having a general capability of doing that would be awesome.
Exactly. So that's sort of like next up on our list of to-do items as well, to sort of like make that a little bit more generic so that other decorators can sort of like rely on it.
See,
So
sorry.
I have a question about the.
I have a question. One of the challenges you mentioned were the availability of compute. Then in another slide, you mentioned you have basically are dealing both with data centers and the cloud. So my question is, when you talk about compute, is it that in the data centers that you're working with, you don't have GPU availability, and then you have to like fall back onto the cloud, and because some team members are reserving more than they need, which is why they're running into issues?
I think that there's sort of in the sort of off the data centers that aren't GCP, there's a fixed quantity of stuff, right? There's a certain amount of GPU capability available, and a lot of this is actually solved by using Q and being able to preempt jobs that meet certain criteria.
Gotcha. So from your perspective, data centers are basically the cloud data centers, not your own data centers that RAI might be running.
I know it's all, my perspective, they're all the same, right? We have instances. So from Metaflow perspective, there's only one Metaflow service, and that is in GCP, and it connects to all of the sort of on-prem or the other data centers, right? And on each one of those data centers, we have Argo workflows running and Q and all the stuff, right? I think that the resource allocation thing is primarily solved by either buying more GPUs and or using Q to make sure that things are fairly distributed and people aren't over subscribing or running things for a long time.
Gotcha. Makes sense. Thank you.
Yeah. Stop presenting. Yeah, any other questions?
How are you currently working around the dynamic decorator issue, where you can't provision the resources?
So a few things. So like, for example, with cluster creation. So if we want to, so like if we wanted to create an array cluster and have that be dynamic, that's handled by basically hitting an API that we have that will handle the cluster creation for us. So we can make a determination in the step about how much compute we might need. So, and then we hit this sort of API that that will create the cluster and provides, allow stuff to run. It would be awesome if we could kind of deprecate a lot of that functionality, but right now we need it, especially since we have a sort of like CLI attached to that, so people can run, create clusters and run jobs without even using Metaflow at all. With regards to another way that I think that we've handled this is with like nested flows, I think, where you'll have like a parent flow that might determine some stuff, and then it'll create a sub flow that will have certain parameters passed in based off of the parent. But it's kind of annoying well, it's not annoying, it's just like it's hard to communicate to someone that you have to do this, like, instead of it just working like everything else works.
Yeah, totally. No, that makes sense. Off the top of my head, I'm not actually sure which orchestrators support this dynamic thing, because most of the time you have to define the DAG upfront.
I think that folks that I work with have said that you can do this in Airflow somehow, but I don't know if that's actually true.
Good to know. All right. Any else with questions? If not, well, thank you so much for presenting, Louis.
Yeah,
I'll let you know when
thanks.
the recording is available on YouTube.
Great. Thank you.
All right.
Bye.
Thanks, everyone. Bye.